Cutting tools, such as drills, milling cutters, taps, indexable inserts, or similar, can remove material because they have cutting edges. These edges are created by grinding a geometrical shape into the tool blank, which consists of high-strength materials that we call the substrate. Substrate and geometry determine how well cutting tools function. Different materials can be machined with cutting tools. The nature of these materials and the machining speed subject the cutting tools to different loads and wear. Worn tools impair the quality of the workpiece and inevitably need to be changed out more often. The machining industry tries to avoid both rapid wear and retooling as long as possible. The properties of cutting tools can be significantly improved by applying appropriate coatings. Primarily, the coating increases the efficiency of the cutting process by facilitating both chip and heat removal and improving precision, important factors for the industry. The cutting tool is coated when atoms are transferred from a donor material to the tool. There are various processes and technologies for this, such as arc technology or sputtering. In simplified terms, the former process uses an electric arc that vaporizes the donor material to extract the necessary atoms from it. In sputtering, the atoms of the donor material are removed by bombarding them with high-energy ions. Let's take a closer look at the sputtering process because it is the basis for HiPIMS. The cutting tool and the donor material are placed together in one chamber. This material can consist of different elements depending on the coating. In our example, and for the sake of simplicity, we'll speak only of titanium. All unwanted air particles are removed from the chamber by a vacuum. Gas is introduced into the chamber, which, in this case, should behave in a chemically neutral manner. Such gases are called inert gases, which are mainly noble gases, such as argon. The task of the gas is to obtain the desired atoms for the coating. Its goal is therefore the donor material. This is why the components with the donor materials are also called targets. DC voltage is applied between the chamber and the target. The chamber or a corresponding component in the chamber constitutes the anode or the positive pole and the target the cathode or the negative pole. Electrons move from the cathode to the anode. On their way, the electrons collide with the gas atoms. For this to happen, a certain gas pressure is required, that is, a corresponding amount of gas atoms in the chamber. The gas atoms lose electrons through the collision. They are transferred to an energetically higher state and thus become positively charged gas ions, thus creating a plasma. A certain amount of electrons, the amount of power plays a role here, and also a corresponding number of inert gas atoms are required for the plasma to ignite. Positively charged, the resulting gas ions are attracted by negative voltage. They head for the target. The denser the plasma becomes, the more positively charged inert ions make their way to the target, which has a negative voltage and is now literally bombarded by the impinging gas ions. When the gas ions impact the target, donor material atoms are knocked out of the donor material and now move through the chamber like billiard balls striking each other. The atoms of the donor material hit the substrate and form the desired layer atom by atom. For this to happen effectively, the tools to be coated have to be optimally aligned to the targets with the donor material. The properties of the coating can be specifically influenced by means of certain process parameters. Magnetic fields are generated at the target thanks to permanent magnets installed behind the target. These bend the path of the electrons into spirals so that they hit as many of the gas atoms located near the target as possible in order to ionize them. This creates a high concentration of gas ions near the donor material, which strike the target thanks to the applied voltage. The higher the applied voltage, the higher the energy with which the gas ions strike the donor material. This increases the sputtering rate and the amount of donor material atoms obtained. Here we leave conventional sputtering and take a look at HiPIMS. The electrons excited and swirling by the magnetic fields collide not only with the gas atoms, but now also with the donor material atoms that have been knocked out. As a result, they are ionized, positively charged, and thus can be steered. Negative voltage is also deliberately applied to the cutting tool to be coated, which attracts the ionized donor material atoms. The voltage on the cathode is switched off at the right time so that the ionized donor material atoms do not have to decide between the negative voltage on the target and that on the cutting tool and move toward the tool as intended. The ionized donor material particles now bombard the cutting tool and layers grow which are more adhesive, smoother and denser than those made with conventional sputtering. Ionizing the donor material atoms thus has a positive effect on the coating process and on the coating quality. The logical consequence is to generate a denser plasma than in conventional sputtering in order to achieve ionization of the donor material. This is done by using more energy. HiPIMS means high-power impulse magnetron sputtering. But it also means more energy. Much more energy. However, more energy on the cathode also generates more heat. To prevent the target material from overheating and even melting, the energy in HiPIMS is discharged only very briefly, a few microseconds. Conventional sputtering means low average power. HiPIMS means high power peaks followed by power pauses. Special power supplies and current storage devices are required to provide the necessary power. Capacitors provide the energy required for the high voltage peaks. These are charged over a certain time and release the energy to the cathode as a short discharge. A variety of events are now taking place in the chamber. Electrons generate positive inert gas ions that are directed towards the target by the negative voltage and blast off donor material atoms. These atoms are ionized by the electrons in the plasma itself and directed there because of the negative voltage also applied to the cutting tool. The processes take place with a time delay. When and how this delay occurs is decisive. Once you have mastered how to control these processes, almost any element can be used with HiPIMS, for example, by adding aluminium and/or silicon. And this means the possibilities for coating are nearly infinite. You can control the properties of the individual coatings precisely. And, in turn, you can optimize the properties of very different cutting tools. When titanium is machined, for example, for medical implants, HiPIMS-coated tools ensure that the machined parts have very smooth surfaces, an essential property in such applications. Or when rails are machined, where a lot of material has to be removed, the HiPIMS technology delivers layer thicknesses of up to 12 microns.